Watching TV and movies can be a really good way to pass the time, especially when you're in denial about burning out again.
Depressed? I'm the furthest thing from depressed.
But when you're a technical person, it can also be frustrating. Often I'll see something and I'll go, well, surely that can't happen.
There's a reflection of the man's face.
But when I look it up, I often find out that something like that could happen, or it could have happened a few decades ago, or it couldn't at the time, but it could now because of new discoveries and inventions.
I call it the thinglonger.
Either way, I always learn something, and I thought I'd share with you what I learned while watching the 1993 X-Files episode Ghost in the Machine. X-Files is a show about supernatural phenomena. We've got FBI agent Fox Mulder. He's a believer. He believes that the government is hiding the truth from us, that aliens and UFOs are already among us. And he works in a basement without windows or heat, and he's only assigned cases that the FBI cannot explain through other means. Dr. Dana Scully works alongside Mulder, and although she has a lot of respect for him, she believes that there's a rational and scientific explanation for everything that's going on, even when things look really, really fishy.
Mulder, you've been through a lot. More than I think even you realize.
That tension is kind of the core of the whole show. It's what makes it really work. Together, they argue a lot, they put themselves in danger, and occasionally they save 1 or 2 lives. In Ghost in the Machine, which is season 1, episode 7, if you want to watch it, Mulder and Scully help investigate the death of Benjamin Drake, co-founder of Eurisco, a non-specific technology company that makes US dollars, or at least they try to. So in X-Files, we often know more than the protagonists. In this episode, we see Drake arguing with Brad Wilczek, the other founder of Eurisco, who's already been pushed out of the company, but he's worried about the fate of his research baby, the COS.
You saved a soundbite for the press.
Let's not relive the stockholders meeting again.
Don't you get it? You're killing me. You're killing my company.
Eurisco is not your company, Brad. Not anymore, and you damn well better grow up and get used to it.
You're gonna regret this.
After Brad storms out, we see Drake writing up a report about the new direction of Eurisco. Then, as he's about to head out, he notices there's water leaking out of the bathroom. Upon further inspection, the sink is overflowing, and as he tries to shut it off, he receives a call telling him what time it is. And the door closes on him, and oh no, his card doesn't work. When he swipes it, it's nothing. So of course he takes out his backup key, inserts it into the keyhole, and... I'm not sure if it's the electricity that kills him or if he just cracks his head open on the bathroom mirror. Either way, R.I.P. Drake. So our FBI agents arrive at the scene and they learn that Brad's invention, the central operating system, is controlling everything in the building, including the sinks, the phones, and the doors. Due to the way that Drake died, they conclude that someone must have messed with the COS to get rid of him. Except, apparently Brad invented, built, and set up the whole thing pretty much himself.
Could someone have hacked into the system?
Well, not your average phone freak, that's for sure.
And he doesn't make a very convincing suspect.
Could you have done it?
Of course. I designed the system.
Eventually, we find out that nobody messed with the COS at all. The system was just acting in self-defense. Now, we're not going to discuss whether or not an AI going rogue is realistic, because nowadays, honestly, I'm not so sure. What I want to dig into is the FBI's explanation of how the killing went down.
See here? Someone has tampered with the servo. They switched the ground to the negative so that when he put the key in the lock,
You completed the circuit.
it's fused. It takes a lot of juice to melt a steel key.
And to throw a 180-pound man 10 feet.
The servo switch, could it have been moved manually?
We didn't find any prints in the surrounding area.
Ah, there we have it. Delicious TV mumbo jumbo. Now remember, I'm not trying to feel smarter than TV writers. They're just trying to make us feel. And if they need to arrange reality a little, I'm fine with that. I just got very curious about the specifics of what they're saying here and whether it made any sense at all. To do that, we have to learn a bit about how electricity works. Okay, here's a simple circuit. At the bottom here we have a DC or direct current power supply. There's a difference in potential across its two terminals, and so if we complete the circuit with some load, here it's a lamp, current will flow from one terminal through the lamp and go back to the source. DC is what we use to power computer components. It's what your computer power supply outputs. Its input takes AC or alternating current. The reason we get AC delivered to our homes instead of DC is complicated. My understanding is that transporting DC is technically better, but it's also a lot more expensive, so we only use HVDC for long distance interconnections. Back to our circuit. With AC, the difference in potential varies from positive to negative at a certain frequency, and so the current flows back and forth in opposite directions. If we plot the voltage across the live wire and neutral wire, we sometimes see a beautiful sine wave. But it's not always the case. Sometimes it's a gnarly square wave or a triangle wave or really any wave shape that goes positive and negative at regular intervals. Now, in both cases, whether AC or DC, the circuit has to be closed for anything to happen. If we disconnect one of the terminals, there's no path for the current to return to the power supply and no energy is transported at all. Here's the thing though. The circuit doesn't need to be made of wires. If you put those two wires in soapy water or salty water, there'll be high resistance, but some current will still pass. And with high enough voltage, electricity can even pass through air. That's an arc. The higher the voltage, the further it'll jump. So how can we hurt humans with electricity? Well, if you touch both the live wire and the neutral wire, and the circuit's running on 120 volts AC, like in the US, even with dry skin, which makes you a poor conductor, electricity will run from the live wire through the lamp, through you, possibly through your vital organs, and back to the source through the neutral wire. And then here's what happens. For currents over 10 milliamps, your muscles will contract, which can prevent you from letting go of the live wire. If the current is high enough, it can cause a violent spasm and propel you many meters away. If a current over 50 milliamps passes through your heart, it can cause instant cardiac arrest. Think of it as a reverse defibrillator. A current of over 100 milliamps passing through your body may cause serious internal burns, which may require amputation of the affected limbs. Finally, electricity can cause long-term damage to your nervous system, your eyes. With enough current, you can destroy pretty much anything. And yes, you can definitely melt a steel key, although this requires a lot of sustained current. This is all pretty terrifying, okay? I would be lying if I said I hadn't been scared of high voltage ever since I learned about it. Luckily, it's already killed a bunch of people, so we humans have been thinking a lot about how to make it safer. Not all home appliances need the same amount of energy, so our homes have different circuits that are rated for a different amount of amps. For example, a toaster may draw 9 amps, and so it should do fine on a 10 amp circuit. What makes a circuit rated for 10 amps? Well, there's the thickness of the wires, but also such a circuit will have a fuse or a breaker. And if there's a short between the live wire and the neutral wire, then the fuse will melt or the breaker will trip, and that'll open the circuit, shutting the whole thing down safely. But that's not enough. If currents start going out the live wire, through your body, through the ground, and back to the source, because of the high resistance of that path, it may draw less than 10 amps, but still be very, very deadly for a puny human. And that's where the third wire comes in, the ground wire. Now, grounding does a lot of good stuff, including lightning protection, but I'm not going to talk about that. Many electric appliances have exposed metal. This is a problem because metal is a very good conductor. So if the live wire were to come into contact with that metal and a human were to touch it, they would be in serious trouble. So we always ground exposed metal bits like casing, control panels, etc. And by ground, I mean literally connect to the ground wire, which is literally a wire that goes to the ground through a ground rod or metal pipes. The neutral wire is also connected to ground at the main electrical panel and at the final stepped-out transformer of the supply, and that ensures that there's not a big potential difference between the neutral wire and the ground wire, which should make touching the neutral wire relatively harmless in a perfect world, but we don't live in a perfect world, so don't touch the neutral wire. And what that does is, if the live wire touches the metal casing, it will give a path for the current back to the power supply through the ground wire instead of through you. Since the path through ground is very low resistance, it'll look like a short and the fuse will melt or a breaker will trip, and again the whole circuit will be shut off safely. Modern electric installations have one more safety feature that's called GFCI or RCD depending on where you live. Remember that during normal operation, current goes out the live wire and back in through the neutral wire. If there's current going out the live wire, but not as much current coming back in through the neutral wire, then something's up. The current's going somewhere. Maybe it's going through a human and into the ground, like if they dropped a toaster in the bath or something. So a GFCI or RCD breaker will detect that difference in current going out and coming back in and cut the circuit open. This saves many lives, and unfortunately it's not a standard everywhere yet. Okay, now that we know a little about electricity, and I hope my explanations weren't completely wrong, let's examine the way Drake died again. The way Drake jumps back when he touches the keyhole makes it seem like a lot of current is flowing through him. For that to happen, the keyhole and by extension the circuit have to be connected to high voltage. But we can tell that this isn't the case by taking a closer look at the board itself. Notice how it's made up mostly of chips, a few small resistors, and a couple switches and LEDs. Now, there are circuits that deal with both high voltage AC and low voltage DC. A good example is a USB power supply. Here's one from IKEA opened by bitclive.com.
Seems quite well designed. It's got good filtering, it's got the inrush limiting, it's got the modest beefy little heatsink on a supported heatsink. It's not just flapping loose, as is this side and the other side for the diode. It's got the good separation gaps, spark gaps. It's got a slot through between the mains and the low voltage where the windings come off. And the transformer itself seems to be quite sensibly made, and it's got the support circuitry and the capacitors are mounted away from the heatsink. So, you know what? This looks okay.
You can see there's big high voltage capacitors, inductors, and a transformer, and the high voltage part and low voltage parts of the circuit are separated by a big gap. But let's assume I'm wrong and there actually is high voltage arriving to the circuit. Let's also assume that whoever made that circuit is a walking hazard and that they added a switch that somehow flips the keyhole from being grounded to being connected to the neutral wire. What would happen if Drake touched the key? Most probably not much. I like that they made COS leak water all over the bathroom floor because otherwise Drake would be pretty well isolated from the ground since he's wearing shoes. But remember, unless there was a serious wiring problem in the building, the potential between neutral and ground should be very small. Electroboom measured the voltage between neutral and ground in his house and found 0.2 volts AC. And here's the kicker. Even if somehow that board was high voltage, there was a murderous switch on there, and the wiring of the building was so messed up that there was a high potential difference between neutral and ground, GFCI has been mandatory in North American bathrooms since 1975. If Drake did complete the circuit, the GFCI would notice and trigger almost instantly, saving his life and ruining the episode. Well, that's it for this video. I hope it was accurate enough. This took a lot of research to make, and I'm still not sure I got it right. Either way, this was fun to make, so I hope you enjoyed it, and if you did, please like, comment, and subscribe. And I'd like to thank my Patreon subscribers for supporting me through the creation of this content. As always, I couldn't do this without you. Stay awesome, and until next time, take care.
But there's plenty of kooks out there, data travelers, electro wizards, techno anarchists. Anything's possible.